this is Captain Chaudhari. I want to do one more SFBM question for you with some variation. So this is a uniform beam that is 8 meters long. So let's name this beam as A, B, C, D, E, F, G, H, I. Now this beam is supported at a point support or knife edge on one side, and it is supported on a flat platform over here, right? The weight of the beam is 80 kg, and between the point E and G, that is 4 to 6 meters from left end, you have spread a weight that is uniformly spread, and that amounts to 100 kg. The SFBM diagram we are expecting to be different than what we did in our last question, because here we have a support that is flat support. Now we cannot say that the beam over here is touching at this point, this point, this point. Some assumption we have to take, and we assume for the calculation, for initial calculation, we assume that the reaction point is at H, which is halfway between G and I. And we also assume that this 100 kg weight is acting from middle, that is F. And we also assume at the time when we take the moments, we also assume that the entire weight of this beam is acting from the midpoint. So once again, the total weight is 180 kg. Can I say that RC plus RH, RC plus RH is equal to 180 kg. This is equation number 1 of equilibrium. And I always told you, you take the moment about the left support, we assume that the beam can turn about this point. What are the clockwise turning moment? Let us look at them. And what is the anti-clockwise turning moment? So clockwise turning moment is 80 working from 2 meters from C, and 100 acting at 3 meters from C, and this total clockwise moment should be equal to anti-clockwise moment, and that is RH multiplied by 1, 2, 3, 4, 5. So this is 160, this is 300 is equal to 5 RH. This means 460 equal to 5 RH. This means RH is equal to 92 kg. And if RH is 92 kg, then RC should be 180 minus 92, that is 88 kg. So we note down the values here. RC is equal to 88 kg and RH is equal to 92 kg. Now let us start finding out what is the shear force value. We are writing in terms of kilogram, and the points are A, B, C, D, E, F, G, H, I. The method is same. We put the screen and find out what is there on the left of it. Left of A is this nothing, so SF at A is 0. B will be minus 10. C will be minus 22. There is a transition because at C the reaction is 88. So minus 22 plus 68 it will be, because up to here is minus 20 and suddenly there is an addition of 88. So 88 minus 20 is 68, and at D it will be 58. At E it will be 48, right? At F, what happens is, at F compared to 48, there is a reduction of 10 as well as 50, because half of 100 is 50. So we have to reduce 60 from 48. That will give you minus 12, and similarly at G it will be minus 12 minus 10 plus 50. So that will be minus 72. Now what happens at this point H? There is a downward force -10 and there is upward reaction half of 92, that is 46, which means that at H we will have to do -72 -10 plus 46. So that is -82 plus 46. That will give me -36. And then you have -36 at I, you have -36 -10 plus 46, and that is 0. So we have these values of shear force, 0, -10, and then finally the final value of shear force is also 0. We'll try to draw the curve. Okay, now this is a beam that is 8 meters long. This is A, then B, C, D, E, F, G, H, I. Now the maximum value upwards is +68 and downwards is -72. So we can take a scale now. We may take the length scale as 2 meter is equal to 1 centimeter, or we can even take 1 meter is equal to 1 centimeter, right? So we will not go for the proportion here. The shape has to be same, but the dimensions might be different. So just for the convenience, you may say that just for making it more clear, you may say that the scale of length is equal to 1 meter is equal to 2 centimeter, and the scale of SF, you can say 10 kg is equal to 1 centimeter. So 10 kg is equal to 1 centimeter, so 10, 20, 30, 40, 50, 60, 70. This is shear force and the unit is kg. And then on the negative side we have -10, -20, -30, -40, -50, -60, -70, because it has to go up to -72. So from A, which is 0, we go up to -20 at C, and then it jumps to +68, and thereafter at E the value is 48, 10, 20, 30, 40, 48. This is the value at E. It comes this way, and at G the value becomes -72. It becomes -72. That means the curve would come like this, and from here it rises to 0. So this is the shear force curve. So you can see that the shear force curve starts with 0 at A, and as we proceed at B, the force to the left of B is -10 because it is downwards, and -20 up to here, and suddenly it changes from -20 to +68 because there is a reactional force 88 kg upwards, and then from 68 it becomes 58 here, 48 here, and in this area, this 1 kg, there is a downward force of 10 kg and 50 kg, total 60 downwards. So when we subtract 60 from 48, it becomes -12 up to here, and once again -12 -60 becomes -72 here, and at this point there is downward force of 10 kg, but upward reaction equal to half of 92, that is 46. So there's upward change by +36, and after -36 you have -10 here and +46. At end we have the shear force equal to 0. The curve is this way. The parallel run over here and here indicates the stretch of the uniform beam. The vertical stretch indicates the point force. Point force in this particular question is only at one position, that is C, right? So if a candidate draws the curve in a curvilinear fashion, that means he does not have a correct idea of shear force and bending moment. So the curve must be a straight line. It is not curvilinear. The curve must be a vertical line because there is a point force, and you can see that the slope suddenly increases drastically, and that is because of the extra spread weight on top. And unlike the previous curves here, you would see that the SF curve is also running upwards. So we'll see how the shape of the bending moment curve changes in this question. Now let's calculate the BM values. The unit we have used for the BM is kg meters. At A, the bending moment is 0. At B, as I told you, fix this point, and this force of 10 kg is trying to bend the beam in anti-clockwise manner. Anti-clockwise to the left of point under consideration is negative, so it is minus 10 into half, that is minus 5. At C, it is minus 20 into 1. We have done this before, minus 20. At D, it is minus 30 into 1.5, that is 3 meters of beam, that is 30, and the center of gravity 1.5 meters from D. But another clockwise moment is given by RC, that is 88. So we'll also have plus 88 into 1. Let's put these values. 88, and this is minus 45. 88 minus 45 gives me 43. This is 43. At E, it will be minus 40 into 2 plus 88 into 2. So that is 88 into 2 equals minus 80. Gives me 96. And at F, there is this point F, you have minus 50 into 2.5 plus 88 into 3. But we have at F, we have this 50 kg downwards, that means anti-clockwise moment, at a distance of half a meter, that is minus 25. So the total is 50 into 2.5, this is negative, plus 25. The total negative is 150, it is minus 150, and the positive value is 88 multiplied by 3, that gives me 264. Resultant is 114. Let's see what happens at G. So at G, it is minus 60 into 3 plus 88 into 4, and then if we consider G as pivot point and we are looking at this 100 kg, the contribution of 100 kg is minus 100 into 1. So 60 into 3, 180 plus 100, that is minus 280. And then you have 88 into 4. 88 into 4. The positive value is 352 minus 280 gives me 72. At H, it is minus 70 into 3.5 plus 88 into 5 minus 100 into 2. And there is this reaction, no? Half of the reaction is 46. 46 into half plus 46 into half gives you 18. So this value is 18. Lastly, we have minus 80 into 4 plus 88 into 6 minus 100 into 3 plus 92 into 1. So the negative value is 320 and 300. 620 minus values and positive values. 88 into 6 gives me 528 plus 92. 620 plus 620. The total becoming 0. So that confirms that our BM is calculated on the right track. Okay, let's decide the scale now. Now the maximum value we are expecting close to F, and that means we need to make a curve so that it accommodates 114 or so. So we can take a scale of bending moment as 20 kg meters is equal to 1 centimeter. So it becomes 20 here, 40, 60, 80, 100, 120 and so on. We start with 0 and bending moment at B is minus 5. So this is minus 20, minus 5 would be so close over here, and then at C it is minus 20 over here. So the curve would go like this, curvilinear, and then the value at D is 43. Value at E is 96. Then you have 114 at F. And then at G it is at G it is 72. And then you have 18 at H. It is 0. Now the most important thing here which you will witness is two things should be correct in this curve. I have drawn this line to show that on this side of this line the curve will have center of curvature downwards, but in this portion, because the SF curve is going upwards, the center of curvature should be upwards. That is one thing. And second thing is, wherever this SF curve is changing the direction, you will have the peak value. So when you're drawing the curve, make sure that the peak value happens at the point of intersection, right? And it is curvature up to here, the convexity is up to here, and then the concavity starts. This is how you have to draw the bending moment curve, right? I hope you have considered these three very important points. Wherever SF curve is changing direction, the bending moment will have peak value. If the SF curve is running downwards, you will have convexity this way, that means center of curvature is down. If the SF curve is going upwards, you will have the concavity this way, that is center of curvature upwards. And also, although you see the negative SF area looks to be equal to positive SF area, the bending moment curve is not like that. The entire bending moment curve may be positive, or entire curve may be negative, or it might be mixed. So the maximum bending moment which we have can also be found by adding up the area under the curve up to this point, you know, the algebraic sum of the area. That means this area is positive, from there you subtract the negative area, and whatever is the resultant value, that is the bending moment at this point, right? That means the maximum bending moment which is occurring at the intersection of the SF curve and the x-axis, the value, whatever it is, I have shown here in kilogram meter, right? And suppose you are required to state what is the bending moment value at F. So bending moment at F is 114 kg meters, but strictly speaking, kg meter is not the correct unit to state for the bending moment. The correct unit would be Newton meters. So what I do is 114 into 9.81 gives me 1118.34 1118.34 kilogram Newton meter. But you need to state like what kind of bending moment it is. Like you can't say plus or minus. No plus or minus. That is our sign convention. But as per our sign convention, wherever the bending moment curve is in positive side, it means sagging. So maximum bending moment is happening at this point where the SF curve is changing direction. And if you want to know what is the bending moment at F, I can say 1118.34 Newton meter sagging. Because as per our convention, the positive bending moment means sagging.